So we looked at GPS as an example of a location sensor. Now we will look at rangefinders. Rangefinders are sensors that measure the distance to nearby objects. So if this is my sensor S and here's my object O, then this sensor if it is a rangefinder, can measure this distance D between itself and the object. There are various kinds of rangefinders. Some of them are rangefinders that are based on stereo vision, that rely on sonar sensing, and another category of rangefinders is the optical rangefinders. Now within optical rangefinders we have ToF cameras, time of flight cameras, and then scanning lidars. So ToF cameras are used for detecting the distance with the objects that are very close. Say for example detecting something like a human hand, whereas scanning lidars are for detecting objects within say around 100 meters or so. The next category of rangefinders are radars that are for much longer distant objects distance detection. Most ground robots today are equipped with some kind of optical rangefinders, and within optical rangefinders mostly scanning lidars. Now let's talk about sonar sensors and stereo vision. Let's just start with sonar sensors. What sonar sensors do is they emit directional sound waves. So they need a medium to send the sound waves. So they basically send these sound waves, and these sound waves are reflected by, if there are objects, reflected by the objects with some sound making it back to the sensor. So if this is my sensor S, and let's say these are various objects in the scene, then what the sensor will do is emit sound waves into the environment, and the hope is that some of the sound will strike the object and make it back to the sensor. And the time and intensity of the returning signal indicates the distance to the nearby object. So if this returning time is very quick, then that means the object could be very close to the sensor. That's why the sound came back very quickly. And then also the intensity of the sound wave, that is how much of it was absorbed by this object, will also give us more information about whether the object is moving or not, or whether how far the object is, and so on. And sonar is the technology of choice for AUVs, underwater vehicle, autonomous underwater vehicles as well. Many existing biological creatures like dolphins, bats, use something known as echolocation. That is, what they do is these creatures send out signals to the environment, collect the signals back, and by looking into these, by analyzing the time and intensity of the returning signals, they sort of create an image of the environment. That is, they have a sort of a picture of the environment by just looking at these returning sound waves. Interestingly, we humans can also do this echolocation, and this is particularly of interest to blind people, those who can't see. And it turns out that we can adapt ourselves to learn echolocation and then sort of behave as, or like, to act as a sonar sensor ourselves. Here's an example of Daniel Kish.
At first glance, this may seem like an ordinary man out for an ordinary bike ride. But look and listen a little more closely. Daniel Kish is completely blind. In fact, he doesn't even have eyes, save for prosthetic ones. Daniel has never seen a tree, a car, or even the bicycle he's riding. So how does he know where he's going? Or how to avoid oncoming traffic? The answer can be found in the clicking sound you hear. It's called echolocation. Bats use it to fly around in the dark, and dolphins use it to navigate the oceans. Daniel uses echolocation, or sound, to see.
Every environment has its own acoustical signature. Every surface has its own acoustical signature.
Next, let's look at stereo vision. So the idea behind stereo vision is that you have multiple cameras, let's say camera C1, another camera C2, and then we have this object. So this camera takes picture of this object, another camera takes picture of the same object. So there are two cameras, and then they take, or they sort of like they image the environment. They understand the environment from slightly different viewpoints. So if you have two cameras at the same place, then that doesn't become stereo vision. But if they are slightly away from each other, then that gives you multiple perspectives of the environment. And this resulting parallax, that is like the comparison of your image one and image two, can be used to compute the range of the surrounding object. So this difference between these images can tell us whether the object is moving at a particular direction, or how far the object is, and so on. This is also the principle by which our human eye works. So with our eyes, we can perceive the depth in the scene in our 3D world, because two eyes produce different perspectives of the world, and then by comparing these two images, we can perceive depth in the 3D world. Now, for mobile ground robots, that is, say for example, autonomous vehicles, cars and trucks, etc. These two techniques, these two sensors, that is sonar sensors and stereo vision, are rarely used. They are not very much used, primarily because they are not accurately reliable. There are other techniques that are much more helpful, but there are some examples where people have used stereo vision and other techniques. But sonar sensor, being an active sensor, also there is a lot of chances of signal interference. As an example of optical range sensors, let's look at the time of flight cameras, or ToF. Just like the sonar sensors, all the optical range sensors, what they do is they emit active signals. Now, in this case, instead of sound waves, they emit light to the environment, and they measure the time until the reflection of the signal arrives back at the sensor. And by looking at when your send signal returned back to the sensor, we can calculate the distance between the sensor and the object in the real world. So one example of these optical range sensors is the time of flight cameras, and these are widely used. One of the examples of time of flight cameras is the Kinect for Xbox One. I think it was released in 2013, and it uses a wide angle time of flight camera where you can play in front of this device, and it recognizes your gestures and hand movements and so on, and it processes 2 gigabits of data per second to read its environment. That is, whether you are kicking a ball or playing with something in front of the camera in order to play. Let's look at how a time of flight camera works and what it actually does.
So to start with, let me just show the basic idea here. You can see here with my hand, the Pixel technology is enabling the 3D time of flight as tracking my fingertips, as indicated by the spots on the end of them. It's also tracking which way my fingers are pointing, as well as which way my palm is pointing. Let me turn on one function here just for a second. It's called the centroid function. So the centroid function is actually where you can see the 3D cloud. That is the surface area of my hand. So the software is monitoring each one of those points to determine where my hand is in space and time.
One of the key features of the time of flight camera is that it can capture the full 3D at once. In other words, unlike many other sensors where you sort of do scanning of the environment and sort of process this information to obtain a full 3D model of the environment, time of flight cameras don't do that. They give you the entire full 3D picture at once. That means we don't need to take various pictures and assemble them to form 3D. And usually in ToF cameras, this artificial illumination is provided by either by a laser or by an LED. The main components of a time of flight camera are the lens that it has, integrated light source that emits the light signals, sensors to detect the reflected lights, and an interface to connect the time of flight camera to a power source and to other devices. Now let's look at some of the applications and disadvantages of the time-of-flight ToF cameras. Time-of-flight cameras are very widely used for logistics, that is for box packing, for moving packages inside a warehouse. Now it's very effective inside a warehouse where the environment is much more controlled. They're also used for scanning and labeling items and for autonomous vehicles inside warehouses, not usually in open environments. They're also used in factory automation for finding, picking, and mounting objects inside a controlled environment. Also for many medical applications, for checking patients, monitoring and positioning, etc. Despite many of these wide applications, ToF cameras have disadvantages as well. Multiple reflections produced by corners and concave shapes creates noise. So if you have an environment where there are a lot of reflections like these, then time-of-flight cameras have a very hard time sort of creating a clear or a more relevant picture of the environment. High intensity ambient light confuses the sensors, so that means these sensors don't work very well in open environments, particularly in sunny environments. These cameras don't work very well. Also, if you have multiple time-of-flight cameras, then the signals can disturb each other. So for that reason, you can play ToF camera-based games at your home without any problem because usually there is no interference. Also, the accuracy is only around 1 centimeter. So if we are looking for extremely highly precise accuracy, then time-of-flight cameras don't work very well. But for many practical applications, this accuracy of 1 centimeter works pretty well. Next, we will look at lidars, also known as scanning lidars. The word lidar comes from light detection and ranging. So they basically measure distance to a target object by illuminating the target with a pulsed laser light, and then just like any other active sensors, they measure the reflected pulses with a sensor, and this measurement helps us understand how far the object is. Here's a slightly older scanning lidar that is primarily used to sort of scan buildings, rock formations, etc., to produce a 3D model of the environment. And with the help of the laser that's sent out of this lidar, it can be used to measure the distance to the first object on its path, so that this first object will reflect the light back, and then the lidar can process this information to estimate the distance between the lidar and the object in that scene. Lidars tend to provide longer range than time-of-flight cameras or ToF cameras, and they also perform better in bright daylight, and that's primarily because they use laser lights. Usually 600 to 1000 nanometer lasers are most common for most of the applications, and the maximum power that a lidar can use is limited by the need to make them eye safe. So if you're applying or like using lidar in a place where there are a lot of people, then you usually will use a lower power laser, whereas if you're certain that the environment does not have people, then you can use more powerful lasers and obtain a more higher resolution picture of the environment. Scanning lidars also have disadvantages. One of the key disadvantages is that its computational requirement is very high. The data obtained from lidar need to be pre-processed in order to come up with the full 3D picture of the environment. It is an active sensor, so all the disadvantages of active sensors come with it. Also, lidars do not scan the full 3D at once. That is, they need to do some sort of internal processing to scan the environment. Maybe they have to rotate the camera by certain angle and at certain steps to come up with a full 3D picture. So unlike ToF cameras, they do not scan the entire 3D environment at once. But since they can work at longer ranges, they collect information from much farther objects as well. Scanning lidars have a lot of applications these days, and they're used in many robot-like vehicles or robots these days. These sensors are used in agriculture to create topographical map of the fields, such that once the slopes and everything, the sun exposure, etc., are revealed of the farmland, then this can tell us where to apply fertilizers or where to even throw the seeds. So with the help of these lidars, once we have this topographical map of the field, where there is slopes, where there is flatlands and things like that, it helps us plan, um, plan where to apply more fertilizer, less fertilizer, and so on. In other words, this is a very important tool for something known as precision agriculture, agriculture, agriculture. Just like the way we talk about precision medicine, precision agriculture is an area where we want to apply techniques like applying seeds, sowing seeds, applying fertilizers, etc. Very, very effective based on the type of land you have, and so on. So lidars are very widely used for that purpose as well. Many autonomous vehicles these days use lidars for obstacle detection and to sort of for plan the path for the autonomous vehicles and so on. So many autonomous vehicles, almost all autonomous vehicles these days, except for Tesla and a few others, use lidars, scanning lidars, as one of the primary sources of information to collect from the environment. One of the examples is that the Stanley self-driving vehicle, the autonomous vehicle, used 5 lidar units. These lidars were at the time produced by a German company, Ch25, for short-range detection in that robot, which was the winner of the 2005 DARPA Grand Challenge. Also, police officers use lidar speed guns to measure the speed of the vehicles and for speed limit reinforcement purposes. LiDARs are also used these days in many computational devices like iPad. So the 2020 iPad Pro, the 12.9-inch version, comes with a LiDAR scanner, and this scanner is used by many augmented reality applications to scan the environment, like your room, and to give you all the fun things and the advantages of augmented reality. Now, although there is generally a good acceptance that LiDAR provide very good information for autonomous vehicle, Tesla happens to disagree with that. So Tesla is one of those only companies that doesn't use LiDAR for collecting data, while almost all other autonomous vehicles and the companies that make them, like Ford, GM, Uber, Waymo, all of them use LiDAR as an essential part of the sensor suite. Next, we will look at radars, sensors that can measure distance of multiple kilometers. That is, they are the longest range range finders, and they are also the sensor of choice for unmanned aerial vehicles. So, for example, autonomous drones and such devices will use radars to detect the obstacles. And they are also extremely powerful because if any surface can reflect light, then radar can spot it. One of the example applications of radars is that the company Toyota was one of the first companies to develop safety sensing. Their safety sensing technique is known as Toyota Safety Sense, where they have implemented radars to for dynamic cruise control. So even when the vehicle is not fully autonomous, they have cruise control where these radars are installed in the front of the camera that scan the environment. And what these sensors allow you to do is if there is a vehicle traveling in front of you, then based on the reflection from this vehicle, your vehicle can automatically slow down or speed up to match the speed of the vehicle in front of you.